Hello, this is Charlene. We're going to be talking about the library of functions and piecewise functions in this video. It is notable that all of these functions will be the parent function, which means that they will all pass through 0, 0 or be centered by 0, 0, the origin. Um, this first one is a linear function. And a linear function does look like a straight line. The parent function um, increases from left to right. It passes through 0, 0. And we should also note that we could write that as y is equal to x. So we've written it as a function notation. Function is equal to x, but it is the same thing as y equals x. That is the um, equation of that line is y equals x. So that's the first function. What else do we have? We also have, they're actually referring to this as the squaring function. I typically do not call it the squaring function. I call it the quadratic function, and it is noted by y is equal to x squared. That's how we know that a quadratic is because it will always have a power of 2 as the highest exponent on the variable. And of course, the graph of a quadratic is a parabola, and the parent function is just the U-shaped. It's a positive. If it was upside down, that would be a negative x squared. So those are little things that you have maybe seen about these, but hopefully you can be reminded by this video. What else do we have? We have an absolute value function. The absolute value function looks like a V, and as I said before, they always touch on 0, 0 at the origin. This is f of x is equal to the absolute value of x. We can also write that as y is equal to the absolute value of x. Okay. We have the square root function. Okay, the square root function, f of x is equal to the square root of x, can also be written as x to the 1/2 power, and it starts at the origin, and then it goes to the right at a slight slope, and it is a square root function. Okay, the last one, actually, I'm not sure if that's the last one. They're calling it the cubing function, but I tend to just call it just the cube function. And of course, it's f of x is equals x cubed. You can also write that as y is equal to x cubed. And it is this nice little curvy line. It increases from left to right, and it also passes through the origin at the center of the x and y axis. Okay, cube root function. Cube root function, of course, is y is equal to the cube root of x. And of course, that can also be written as x to the 1/3 power or to an exponent of 1/3. And this one looks like the cube root, except it's laying on its side. The cube root function is laying on its side. And again, it also passes through the origin at 0, 0. Okay, so this is the last one we're going to talk about today. There are other functions, but these are the primary ones. But it's really important that you kind of know ahead of time what these functions look like, because your work will be a lot faster. The cube root function is not as common, but the cube root is very common. Square root, depends on what you're doing. It can be very common. The absolute value, knowing that it looks like a V, that is to your advantage to know these things. Quadratic, that looks like a parabola, knowing that it's a quadratic because it has an x squared term. All these things are things that you should familiarize yourself with, understanding what a linear function looks like, that it looks like a line. And of course, y equals x is also which should remind you of y equals mx plus b. This is our favorite. This is our favorite linear function form, just because it's easy to graph a line if it's in that form. But you should also understand all of the parent functions. It makes your life a lot easier and makes quicker work when you understand what your parent function looks like. and then you can move from the parent function to create transformations from the parent functions. Okay, let's go ahead and start talking about piecewise functions. Um, says when graphing a piecewise function, graph each piece separately, noting the restricted domain. Use a table of values and note open and closed circles at each endpoint. Okay, so we are going to evaluate each piecewise function at the given values of the independent variable. Okay, so the first thing that we definitely should look at are our restrictions. These things right here are the restrictions on each piece of the piecewise function. So this one says that x must be less than 0. And this next restriction says that x must be greater than or equal to 0. So that's the first thing we have to consider. So here they want us to evaluate f of -3. That means that they want us to put -3 into our function. So again, we have to say, okay, does -3 fit into this restriction? Or does -3 fit into this restriction? So -3, is it less than 0? Yes, it is. So that means that we need to put this -3 into this piece of the function. So that's what we're going to do. We're going to do 6x minus 1, and that is going to be equal to 6 times a -3 minus 1. And that is equal to 6 times -3 is -18 minus 1, and that is equal to -19. So the um, piece of the function evaluated for -3 is equal to -19. So we would write this down here. The function when x is equal to -3 is equal to -19. Okay. Okay, let's go down here. Okay, so we're looking at the same function, but now we're going to evaluate it for 0. The x will have a value of 0. So we need to decide which one. Is this going to go with the first restriction or the second restriction? Well, it says it's 0. So this one right here says it's equal to 0. So that means this time I'm going to put 0 into this piece of the piecewise function. So 7x plus 3 is going to be equal to 7. X is now going to be equal to 0 plus 3. And so that means that our function evaluated for a value of 0 is equal to 0 plus 3, which is going to give us a final answer of just 3. So the function value at 0 is equal to 3. Okay, we're now going to evaluate our piecewise function for um, an x value of 4. So again, which restriction does 4 fit into? Is 4 less than 0? No. Is 4 greater than or equal to 0? Yes. So that means I am going to put my 4 into this piece of the function. Okay, so that's going to be 7. X is going to be equal to 4, and then plus 3, and 7 times 4 is 28, plus 3, and 28 plus 3 is equal to 31. So our function value when x is equal to 4 is equal to 31. Okay. Okay, so we now have a new function to consider. My value is 7, and I need to consider, does it meet this restriction, this requirement, or does it meet this one? So 7 does not equal 5 or 7 equals 0. Well, it definitely does not equal 0, so it would qualify for this piece of the function because it does not equal 5. So that means I'm going to put my 7 into this piece of the piecewise function. So that's going to be 7 squared. Oops. 7 squared minus 45. Oops, I can't talk either. 25. 7 squared minus 25. And that is going to be divided by 7 minus 5. And that is going to be equal to 49 minus 25 divided by 2. And 20, let's see, 49 minus 25. Let's move it down here. That's going to be 24. 24 divided by 2. And then that is going to give me a value of 12, which means that my h function, when x is equal to 7, is equal to 12. Yeah. Okay, now we're going to evaluate the same function when the function has an x value of 0. So again, we've got to look at our restrictions on our domain, our x values. And when x is equal to 0, well, it matches up with the second piece. So that means that we're going to, we're going to try to plug 0 in there, but can we plug a 0 into a 10? No, there's no variable there. But what this means is that our h function, when our x value is 0, our function value has a value of 10 only. There's only one value. And of course, we can think of that as being y equals 10. It would just be a constant. Okay. And what else do we have here? Okay, so now we're going to look at our function evaluated for a value of x value of 5. So which of our domain restrictions does it fit into? X is equal to 0 or x does not equal 5? Well, it is not equal to 0 and it is equal to 5, so that is not true. So it does not fit into either one of our domain restrictions. So we would say that this function, that the function h of 5 for this piecewise function is undefined. It does not meet any of the constraints that our domain has on it. So undefined. Okay, we are going to graph the following piecewise function using a table of values. So our piecewise function says that f of x is equal to x plus 2 if the x is less than or negative 3, or our function is equal to 4 if f is greater than or equal to 3. So their table of values set up for the first one. If you notice, here is the restriction, which is essentially a restriction on our x values, which produces our x values, which is the same thing as our domain. So the x less than negative 3, those are going to produce x values. And then the function is the function value. So that's essentially the y values. X plus 2. So I just chose randomly some numbers that qualified as less than negative 3. I chose negative 4, negative 5, and negative 6. All of those are less than negative 3. And then I substituted them into the function here, here, and here. And it gave me values of negative 2, negative 3, and negative 4. And so that produces coordinates that we can plot on our x and y coordinate system. So negative 4, negative 2. So I could do negative 4, 1, 1, 2, 3, 4, and negative 2, 1, 2. So right there, that would be like negative 4 and negative 2. And then I also have negative 5 and negative 3. So negative 4, that would be negative 5, and 1, 2, 3. Okay, and then negative 6 and negative 4. So negative 6 would be right there, and then negative 4. 1, 2, 3, 4. So these are points that are created, but we need to also consider the fact that it said x is less than negative 3. So on the negative 3, it's not equal to the negative 3, but it is going to have a value. So at negative 3, the function value, let's calculate that. Negative 3 means that it's going to be negative 3 plus 2, which is going to be equal to negative 1. So at negative 1, oh, the x value is negative 3. Negative 3, 1, 2, 3, and negative 1. So right there, it's going to be an open circle because it is not equal to the negative 3. And then I can combine those with a line starting with the open circle and moving in this direction. So let's see if we can straighten that up just a little bit. Yeah, I think that looks a little bit better. There we go. Okay, so that's essentially the first piece of the function. That red line right there, that's the first piece of our piecewise function. And now we're going to go ahead and set the second part of our piecewise function in a table. So again, we have x is greater than or equal to 3, and that produces our x values, and our y value will be 4. But like I said, we're going to go ahead and, well, we already did equal to 3. So over here, because it was just less than, I also had to calculate it, but it was with an open circle. This one is going to be a closed circle. So we're going to go ahead and plot 3, 4. So 3, 4, 1, 2, 3, and 1, 2, 3, 4 with a closed circle because it could be, this one can be equal to the negative 3. And then we have 4, 4. So 1, 2, 3, 4, and 1, 2, 3, 4. Yes, it's the same on the same row because this is going to be a constant function right here. It's just the number 4. And then 5, 4 is going to put me right there. So then the same thing, I can add a line right there starting with 3, and it'll just continue on this direction. And like I said, this one is a closed circle. This one's an open circle. So that is what our piecewise function. This is the first piece right there, and this is the second piece. Okay, so that's how we would graph it using a table of values for each piece of the piecewise function. Okay, we're going to do it again. This piecewise function has 3 parts though. So we're going to do our table of values 3 times for all 3 parts. Okay, so for the first one, again, my restriction on my domain, that's where I choose my x values. It says it's less than or equal to 0, so I chose 0, 1, or 0, negative 1, negative 2, negative 3, because those are all less than 0 or equal to 0. And it produces a y value, because that's the function value. This is the function value. The function value is produced by negative x. And it gives me values of 0, 1, 2, and 3. So again, I can plot these as coordinates on my grid. So let's do that right quick. 0, 0, and that is going to be equal to the 0, so that's going to be closed at 0, 0. And then negative 1, 1. And on this one, I have put 2, 4, 6, 8, 10 because one of these graphs goes a little higher than the top of my graph. So that means I'm going to put it at negative 1 and 1, which will be about right there. And then negative 2, 2, that will be on the corner of those two intersecting lines. And then negative 3, negative 3, so it'll be about right there. Okay, so again, I can go find a line put a line headed that direction. Okay, that looks close enough. Okay, and then the next part, I'm going to, again, put the restriction is the x value, and the 9 minus x squared will be produce the function value, because the y is the function value, and it produces points of 1 and 8, 2 and 5, and 3 and 0. So we're going to do 1, 8, 1 and 8 all the way up here. And then 2 and 5, 2 and 5 will be about right there. And 3 and 0 will be right, it's not going to be on, that's 4. So I need to put it right in the middle. Okay. And of course, if you noticed on my graph, I also kind of delineated all the intervals. It's like this was the interval for less than 0, and this is the interval for between 0 and 3, and this is the interval that is greater than 3. So I kind of highlighted those so we could kind of see where each of the parts of our piecewise function are going to live. Okay, and so I need to connect those 3 dots. So here's the thing, is that this one, if I put in 0 right here, then it's going to be 9 minus 0, so it's going to produce 0, 9. But that would be an open circle. That would be an open circle. So open circle right there. But then it's going to connect down to that 3 right there. So just pretend like it's a little bit straighter. It's a little wiggly there, but we'll talk about that here in just a second. Okay, so our third piece of our piecewise function right here. So again, we're going to have the restriction is where we have our x values, and then the function part produces the y value. So I've got 4 and 1 and 5 and 2, 6 and 3. So let's plot those. 4, 1. So 4, 1, and it says it's going to be less than 3. I should go ahead and plot the 3. 3. So it's going to be 3 minus 3, 3, 0. But it's greater than, so that's going to be open circle. So it's going to be open circle, which is already part of this curved line that's kind of sloping down right here. So that one is the one that has a closed circle. This one is going to start there, and then we're going to connect it to 4, 1. So there would be 4, 1, and 5, 2, 5, 2 would be about right there, and 4, let's see, 5, 2, and 6, 3. So 6 and 3. So again, I'm going to find a line, and we will connect it. Let's try to straighten that up just a little bit. Okay, so that is essentially what my 3 pieces are going to look like. Again, this first piece only exists less than 0, right? It only exists less than 0. And then this piece of the graph only exists between 0 and 3. And this third piece of the graph only exists greater than 3. But it will continue. These will all continue. That will continue on, and this will continue. The only piece in the middle will not continue on. It starts right here. It starts right here with an open circle bigger than 0, and it stops and is equal to the 3 right there. But I wanted to just quickly kind of mention something. If we know what kind of functions these are, that's the reason why at the top of the video we talked about the library of functions, because this first one right here, that's just a line. Y equals y is equal to negative x. And so and it's negative means it's going downhill. So that produces this first line. And then the second graph has an x squared in it. So this piece right here is a piece of a parabola. This right here is a piece of a parabola. And then this third is x minus 3, which again is a quadratic, or I'm sorry, a linear function. That's y is equal to x minus 3. So that's linear. So it is just a straight line. And of course, it's going uphill. But I wanted to pull this up and show this version. Let's see here. Order, bring it to the front. Oop, not the right one. Order, bring it to the front. There we go. Okay, so this is what, if we were to draw these functions without any restrictions, this is what they would look like. It would be a full quadratic parabola right here. That would be the full function if it did not have any restrictions on the domain. But we restricted the domain to between 0 and 3, and that's the reason why we only drew this piece of that parabola. And again, this first one is a negative y equals negative x, and that's what that looks like if we draw the whole thing. And then this one right here, y equals x minus 3, means it goes through the negative 3. It's y-intercept, but it has a positive slope. So this is what they look like in full, but this is our piecewise function. So we only have these 3 pieces. We have 1, 2, and 3 pieces of our function based on the restrictions of our domain. And we've got 1, 2, 3 pieces of the domain. Okay, so hopefully this helps you go through the process and kind of think about what it means. And just come back, and if you have any questions, let me know. Okay, bye-bye. This video has been brought to you by Connect the Dots Online Math Tutoring. Before you leave, click on the like button and the subscribe button, and have a wonderful day.